Hello, my people. I hope we are doing well. This is video 3 on the cumulative questions for applications of integration, the sections we did in Chapter 6. This is a problem like the one we did in the lecture where you were given 3 points defining a triangle. In this case, we are given 4 points describing a parallelogram. So let's go ahead and read through the question, and then we'll take a look at what that means graphically, and we'll start working through the problems. Given the parallelogram with the given vertices, answer the following questions. Okay, so the vertices are 2, 3, 4, 7, 4, 3, and 6, 7. Said, find the area enclosed using your knowledge of geometry. Part B is confirm the area in Part A by means of integrals. Part C is set up but do not evaluate the integral for the volume of revolution around y is equal to 0, which is a fancy way of saying the x-axis, right? Set up but do not evaluate the integral for the volume created by equilateral triangle cross-sections perpendicular to the x-axis. Okay. Now, this one winds up. You think parallelogram? Wow, I had to chop the triangle in 2 pieces. If this thing's big enough, I'm gonna have to chop this sucker into 3. Well, the great thing is that the way that it's set up, you don't have to. Okay. Because when you drop the altitude in order to determine the area geometrically, you realize that there is no overlap between base 1 and base 2. It actually chops it into 2 right triangles, which is nice because if you had been given something more akin to, here, if I'd been given a parallelogram that was more like this, then you would have had sort of 3 regions. You would have had one triangle, another triangle, and of course that big rectangle in the middle. Now there are other ways to deal with that, but thankfully on this one we don't have to. We're simply given that. Now, let's go ahead and deal with it in terms of our knowledge of geometry. Now we know that basically the area of a parallelogram, if it truly is a parallelogram, is just base times height, because basically, this triangle right here can be recreated right here. And basically what happens is by sort of relocating it right there, you've basically created the rectangle that it would have been had basically it not been located over here. So it winds up just being base times height. So part A, we know that the area is equal to the base times the height. And in this case, the base is 2, and the height is 4, and therefore the area is 8 units squared. Okay. Now, what we need to do in order to figure out the rest of this is we need to go ahead and figure out the equations of the lines. Okay. Now I want you to notice that the problem itself does not stipulate that the integral in part B has to be by means of x. It doesn't have to be in terms of x, and in fact it's a little bit easier to do it in terms of y. Because if I do it in terms of x, I have 2 different regions of 2 different qualities. Here, and let's go ahead and call this line y1, and this line y2. Now thankfully, it's a parallelogram, so both sides are going to be, parallel and therefore have the same slope. But basically this is going to be y1, and this, let's call this down here y3, even though it's a constant function, and up here y4. So on the interval from 2 to 4, you have to integrate y1 minus y3, And on 4 to 6, you have to integrate y4 minus y2. Well, that's a pain, but let's go ahead and do it. We first, however, need to figure out the equations of the lines. Now, we can go ahead and surmise a little bit in terms of the slope, right? I know, and let me zoom out just a little bit so I'm not so crowded here. I know that in order to go from here to here, I had to rise 1, 2, 3, 4, and I had to run 1, 2. Rise over run, 4 over 2, reduces to 2. So my slope is 2. And so y1, we're going to do y minus 3 is equal to 2x minus 2. Okay, and that winds up being y is equal to 2x minus 4 plus 3, or y1 is equal to 2x minus 1. Okay, well there's our first equation. Let's do y2 now. So y minus y minus 3 is equal to 2x minus 4. Remember, they're parallel, they have the same slope. I was just doing point slope on y1 with this point. I'm doing point slope on y2 with this point. I get y is equal to 2x minus 8 plus 3, and I get y2 is equal to 2x minus 5. Okay, well that helps. Let's go ahead and do this integration. Now, b, let's go ahead and set it up. Like I said, from 2 to 4 needs to be y1 minus y3. So my y1, like I just figured out, is 2x minus 1. My y3 is a constant function. It's just 3. And to that, I need to add my integral from 4 to 6. This one needs to go y4, and that's y is equal to 7. That's another constant function. Minus y2, which was 2x minus 5 dx. Awful lot of trouble, right? Okay, now remember that, like I said, this is y1, this is y3, this is y4, and this was y2, and I'm talking about as it relates to these. Okay, so take another look at that real quick. From 2 to 4, and then from 4 to 6. So from 2 to 4, I'm basically doing this area of this triangle by integration, y1 minus y3 over that interval, and then from 4 to 6, it's going to be y4 minus y2 with the constant function minus the linear from 4 to 6, and that's exactly what I have up here. Okay. Well, let's go ahead and, do what we need to do. Let's go ahead and clean both of these up, and we're going to get 2x minus 4 dx. This one winds up being, remember when you distribute, you're going to need to make sure you distribute to both of them, and this is going to be 7 minus 2x plus 5 when I get the parentheses out of the way. The 5 and the 7 can combine into 12. And from 4 to 6, that is your integrand. Well, that makes x squared minus 4x from 2 to 4, and then 12x minus x squared from 4 to 6. Whew. Okay, now let's make sure I don't mess this up. Okay, let's do 4 squared minus 4 times 4. 16 minus 16, and then 2 squared, 4, minus 2 times 4, 8, okay? And then I need to go ahead and do this one as well, right? I know that this is going to be, this is when I plug in 6, I'm going to get 12 times 6, or 72. So 72, and then 6 squared is going to be 36. And then when I plug in 4 right here, 4 times 12 is 48, and that's minus 16. And so this right here is going to be 0. This is negative 4. Negativized negative 4 is positive 4, right? This right here is 36. This right here is 32. 36 minus 32 is 4. And oh my gosh, will you see? Well, you look at that. 8 units squared. I prefer the geometric method. You could, however, do it in terms of the variable y. And it actually would wind up, once you get the equations for y1 and y2, it winds up being pretty simple. I'm going to show it to you real quick. Now remember, y1 was 2x minus 1, and y2 was 2x minus 5. Now, if I were to rewrite these in terms of x, I'm going to get 1/2 y plus 1/2, and this one, y plus 5, is equal to 2x, and then x sub 2 is equal to 1/2 y plus 5/2. Now, those are simply a way of rewriting y1 and y2. Now remember, y2 is more positive when I'm talking about the y-axis. It is farther away. It has greater x displacement, right? So if we're basically gauging distance away from this axis, y2 is definitely farther away than y1. So basically I'm going to need to do y2 minus y1. Now remember, you also need to do it in terms of your y limits of integration. No longer 2 to 6, but 3 to 7. Okay? And the great thing about this is that if you deal with it in terms of horizontal cross sections and dy and y2 minus y1, there's no partitioning. Okay? It is just straight up y2 minus y1 from 3 to 7. So let's go ahead and see what that looks like. Now remember, everything needs to be in terms of y. So let's go 3 to 7. Okay. 1/2 y plus 5/2 minus 1/2 y plus 1/2. Well, when I distribute this negative, this negative 1/2 y and this positive 1/2 y are going to cancel. This 5/2 and this negative 1/2 are going to become 4/2. So really what you wind up integrating is 2 dy, which becomes 2y evaluated from 3 to 7, which is 14 minus 6, or 8. Yeah, I prefer it in terms of y, but if you don't see it, that's fine. It's obviously still doable in terms of x. I just wanted to go ahead and show you that because, you know, it's fun. All right, so we've done A and B. Let's go ahead and let me zoom back in. Notice that C and D are set up but do not evaluate, okay? Both of them are dealing with cross sections that are perpendicular to the x-axis. So again, I'm going to have to split it up into two integrals. Okay, but it doesn't. You know, that's really not all that difficult, and we can kind of, you know, we can deal with it just fine. So let's go ahead and do that. Now the volume of revolution. Now remember, I'm going to have to set it up in two intervals. But the farthest one away is going to be my big R. So on 2 to 4, my big R is y1. Now remember, you need to square y1 minus the square of y3, which is just 3 squared, okay? So in C, the integral from 2 to 4, now remember your pi, my big R is y1. And y1 is 2x minus 1, and I need to square it, and then my small r is 3 dx. And then to that, I need to add the other washer problem from 4 to 6. Okay. Now, in this one, the constant function is farther away, right? So y4 is basically y is equal to 7. And so y is equal to 7, so it's 7 squared minus y2 squared. So this winds up being 7 squared minus 2x minus 5 squared dx. And that's it. Remember, it was set up, but do not evaluate. Okay? Let's go ahead and do something similar to D. Set up but do not evaluate the integrals for the volume created by equilateral triangles. Okay, so I'm going to have root 3 over 4 out in front from 2 to 4, and root 3 over 4 from 4 to 6. Okay. Now, remember that it is not the difference of squares, but the square of a difference. And because basically the cross-sectional height is basically an expression in terms of the variable for the variable width of a variable side length, okay? And this one is going to be y1 minus y3 squared. So instead of y1 squared minus y3 squared, it is y1 minus y3 squared. And instead of y4 minus y4 squared minus y2 squared, it's y4 minus y2 squared. And those are your integrals for C and D. Set up but do not evaluate. And the reason I did that, I gave those instructions, was because I just didn't want to burn them out, burn off a whole lot of time, and basically make them toil away at arithmetic instead of actually getting done some calculus work and showing me that they understand calculus concepts. That, of course, brings us to the end of our third video. I have a couple more to do, and they're all kind of fun and a little bit different, but it's probably going to be about 6 videos probably, so be looking for those. As always, please do shoot me a message or an email if you have any questions. Bye.